Translations of parent functions. Let's first start with an overview of the different transformations that can occur with functions. The graph of a function can be transformed by either shifting, stretching or shrinking, or reflection. The elementary transformations of a function f are captured in the function notation as follows. For a translation, if you are shifting up or down, it is given by f of x plus k, where k is any number. When you're shifting left or right, it's given by f of x minus h. And again, h is any number. A reflection over the x-axis is given by a negative sign out in front of the function of x, whereas a reflection over the y-axis is given by f of negative x, meaning you're changing the sign of the x values. That's what flips it across the y-axis. We also have what's called distortion. It's also known as stretches and shrinks. You can stretch or shrink a function vertically by placing a coefficient of a out in front of f of x and multiply the entire function by that value. You can also have what's known as a stretch or shrink horizontally, and that's given by f of bx, where b is any coefficient that's put in front of x. We will be exploring each of these transformations, beginning with translations. Now let's discuss vertical shifting up and down. Shifting the graph of a function f of x up or down is given by f of x plus k, and is called a vertical translation. If k is greater than 0, meaning it's a positive number, the graph is going to shift up k units. So if it was plus 2 units, every single point in the graph would move up 2 units. If k is less than 0 or a negative number, then the graph of f will shift down k units. So if I had to go down 1 unit, notice every single point from the original function has been shifted down 1 unit. Consider the function f of x, which is equal to x squared, and two of its translations. We have that g of x is equal to f of x plus 2. If we actually take f of x and substitute it in for g of x in that f of x location, we will get that g of x is equal to x squared plus 2. And notice if we shift f up 2 units, we coincide and land exactly on g. And let's say we have h of x, which is equal to f of x minus 3. Again, take f of x, which is equal to x squared, substitute x squared in for f of x, and we end up getting that h of x is equal to x squared minus 3. And the graph will end up shifting down 3 units. Here's another example with vertical translations. Use the function f of x, which is equal to x squared for each problem below. Given the rule or formula, determine the type of vertical translation that occurs. So for question A, we have that j of x is equal to f of x plus 11. Well, that's going to end up being equivalent to x squared plus 11. Now, what happened between x squared and x squared plus 11? It shifted vertically up 11 units. Now let's look at part B. K of x is equal to x squared minus 2. Well, that's equivalent to f of x minus 2. So that's going to be a shift. Because it's minus 2 and that negative 2 is less than 0, it's going to be a shift downward. So a shift down 2 units. Now let's look at C. M of x is equal to f of x minus 6. If you would like, you can take x squared and substitute it in for f of x. So we have x squared minus 6. So from x squared to x squared minus 6, we are shifting down 6 units. And now the last one that we have is n of x is equal to x squared plus 3. If we compare that to x squared, it's identical, except we have a plus 3 at the end, which shifts the function up 3 units. And here are the solutions to these 4 example problems, and the solutions that appear match the solutions that we found. Here's another example on vertical translations. We're going to use the function g of x, which is equal to the absolute value of x, to graph the translation from each problem below. Then explain in words what type of translation occurs. So p of x is equal to g of x plus 4. So this plus 4 means that we are going to shift g of x up 4 units. 1, 2, 3, 4. So now if we trace this function with pen, it'll be like this. So this is our p of x function. And explain in words what type of translation occurred. We went up vertically 4 units. So a shift up 4 units. Okay, now let's look at q of x. Q of x is equal to the absolute value of x minus 5. So we're taking g of x and it's going down 5 units. So this time the graph shifts down from the parent function. It shifts down 1, 2, 3, 4, 5 units. And here we can see the solutions. We have p of x graphed in blue, and we have q of x graphed in red. And p of x shifted the graph of g of x up 4 units, and q of x shifted the graph of g of x down 5 units, which matches, both of these match the solutions that we found. Here's another example. Use the function g of x, which is equal to the absolute value of x for each problem below. Write a rule or formula for the new function after the given translation. In our first example on this slide, we are going to shift g of x down 8 units. So we're going to have y is equal to g of x, and we're shifting down, so down is in the negative direction, 8 units. You could also rewrite this as y equals, instead of putting g of x minus 8, you could write in what g of x is, the absolute value function. So absolute value of x minus 8. So either of these two answers are acceptable. Now let's look at the next one. This time we are shifting the g of x function up 10 units. So our new function will be y is equal to g of x, up means positive direction, 10 units, or you could rewrite it as y is equal to the absolute value of x plus 10. Both of these are acceptable answers. And here are the solutions to these two example problems, and they do match the solutions that we have found. Next, let's discuss horizontally shifting functions left and right. Shifting the graph of a function f of x left or right is given by f of x minus h in parentheses, and this is called a horizontal translation. If h is greater than 0, meaning you have, for example, f of x minus 1, 1 is greater than 0. Notice this sign does not determine the direction necessarily. Then we would shift the graph 1 unit to the right. If h is less than 0, so let's say we had f of x minus negative 3. Our h is less than 0, it's negative 3. It would be simplified to be written as f of x plus 3. That will end up shifting our graph to the left 1, 2, 3 units in our case. In general, if h is less than 0, then the graph of f of x shifts to the left 8 units. Here's another example of horizontal shifts to the left and to the right. Consider the function f of x, which is equal to x squared, and 2 of its transformations. G of x is equal to f of x plus 2. That can be rewritten as f of x minus -2. And if we wrote it in the function notation and got rid of the f of, it would be x minus -2 squared. So that's why we are moving f to the left 2 spaces, or 2 units, to get to g. Now let's look at h. h of x is equal to f of x minus 3 in parentheses. So our h value is a positive 3, so we're going to move the function f to the right 3 units. It can also be rewritten as the quantity x minus 3 raised to the second power. Now let's go through another example with horizontal translations. This time we're going to use the function f of x, which is equal to 1 over x for each problem below. We are going to write the ruler formula for the new function after the given translation. In our first example that we have, we are going to shift the graph of f of x, which is equal to 1 over x, to the left 2 units. So that means we're going to have y equal to f of x minus -2, because remember, left is in that negative direction. We can then rewrite this as y is equal to f of x plus 2, because remember the minus negative becomes a plus sign. And then if we put it in terms of 1 over x notation, it would be y is equal to 1 over, and then the entire quantity x plus 2. Now let's look at example B on this slide. We're going to shift the graph of f of x to the right 4 units. So we're going this way. So that's going to be y is equal to f of x minus 4. We don't have to simplify anything. So that's going to be 1 over, and then x minus 4 in the denominator. Now let's look at example C. We're going to shift the graph to the left 7 units. So we're going to have that y is equal to f of, and then x minus, and we're going to the left, -7. That is equivalent to f of x plus 7. Oh, that parenthesis should not be there. The x plus 7 is inside of the parentheses. And then if we write it in terms of the function 1 over x, it will be 1 over x plus 7. Now let's look at the last problem that we have. We are going to shift the function to the right 9 units. So right direction is this way. We're going to have y is equal to f of x minus 9. And now we can take the x minus 9 and substitute it in for x in our parent function to get 1 over x minus 9. And here are the solutions to these 4 examples, and they do match the solutions that we found. I am going to rewrite each of these more vertically than horizontally, just for clarification. So the first one is 1 over the quantity x plus 2. Second one is 1 over the quantity x minus 4. Third one is 1 over the quantity x plus 7. And the last one is 1 over the quantity x minus 9. Now let's discuss shifting left or right and up or down at the same time. A translation of the graph of a function f of x is given by f of, and then in parentheses, x minus h plus k. And it includes shifting both up or down with the k value and left or right depending on the h value. So let's consider the function f of x, which is equal to x squared. So our red parabola that we have in the middle there, and 2 separate translations. We have first that g of x is equal to f of x plus 2 plus 1. So remember that f of x plus 2 can also be written as f of x minus negative 2 and then plus 1. So we're going to the left 2 units and then up 1 unit. And that's exactly what this description says. Now if we have h of x, it's equal to f of x minus 3 minus 1. So the h value is positive 3. We're moving to the right 3 and then down 1 unit because of the subtraction of 1 at the end. Let's try an example with horizontal and vertical translations. Use the function f of x, which is equal to 1 divided by x for each problem below. It may help to first rewrite our function f of x more vertically than horizontally. So for part A, if g of x is equal to f of x plus 2 minus 3, what translations occurred? Well, remember, when we have f of x minus h is that horizontal translation. So if it's minus a negative 2, that will end up making that plus 2. And then we're doing minus 3. So we have a horizontal shift to the left 2 units, and we have a vertical shift down because this minus 3 is exactly what movement it has, 3 units. Now let's look at part B. If the function f of x is shifted to the right 4 units and down 5 units, what's the new function h of x? So h of x is going to be f of, it's shifted to the right, so h is remaining positive, so it's x minus 4, and then down 5, so we have minus 5. If we rewrite this, h of x, in terms of the function notation, we're going to have 1 over, and then where the x originally is, we're going to substitute x minus 4 in its place. And then the subtraction of 5 that's outside remains outside. So here's the final function for h of x. Okay, and part C is asking us to graph k of x, which is f of x minus 1 plus 3. So our original parent function, 1 over x, looks something like this. I'm going to first draw our parent function, and then we'll use the h and k to horizontally and vertically move the function. So 1 over x generally looks like this. It's that rational function, and more about these rational functions will be studied later on in this course, but for now just understand the graph shape of the parent function. So it looks like this. So k of x is f of x minus 1 plus 3. So that means this minus 1, h is positive 1. So we're going to shift it to the right 1 unit. And we have a plus 3. That's our k value. So we're going to shift up 3 units. Now, since our reciprocal function has its center at the origin, the easiest way to graph it after transformations is to take this middle point and move it the h and k units required. So we're moving this to the right 1, and we're going up 3. So this is going to be our new center point, and the new asymptotes are going to be x equals 1, and then y equals 3. If we were to rewrite k of x in function notation or as the rational function, it would end up being 1 over x minus 1 plus 3. So that's also why we have our vertical asymptote at x equals 1 and our horizontal asymptote at y equals 3. So again, the quickest and easiest way to graph this new function is to take that center point and shift it according to our h and k values, and then redraw the parent function. So it's going to look something like this when we finish regraphing it. So this is our k of x. And here are the solutions to these 3 example problems, and their solutions do match the solutions that we found. G of x shifted f of x left 2 units and down 3 units. If we rewrite h of x, which is f of x when it is shifted to the right 4 and down 5, it becomes h of x, which is equal to 1 over x minus 4 and then minus 5. And then graph k of x, which is equal to f of x minus 1 plus 3 in the coordinate plane to the right. Here we see its graph, and the function for k of x is 1 over x minus 1 plus 3.